All right, today we're diving into a huge planetary puzzle, and it's one that's going to flip what you think you know completely on its head. Okay, so let me ask you a quick question. If you had to picture the one ecosystem that's the absolute best at locking away carbon, what would you see? I'm guessing for most of you, it's something like a lush, green, tropical rainforest, right? Just bursting with life. Well, what if I told you that picture is actually wrong? The planet's real carbon vaults, the true long-term storage champs, are somewhere you would probably never guess. And figuring out why? Well, that's the puzzle we're going to solve today. So let's get into it. The funny thing is, the puzzle starts exactly where we all thought it would, the rainforest. Because in one very important way, our intuition is totally right. These places are absolute beasts. They have something called the highest net primary productivity, or NPP, of any biome on Earth. What does that mean? It means they are, without a doubt, the world champions at inhaling carbon dioxide from the air and using it to build themselves, to grow bigger, to make leaves, wood, roots, you name it. But, and this is the big but, here's the twist. For all that incredible work pulling in carbon, their soils are actually pretty terrible at holding onto it for the long haul. And that right there is our core mystery. If these forests are basically giant carbon vacuum cleaners, where does all that carbon go? Okay, to get our heads around this, we need to think about it like a really simple budget. Every ecosystem has carbon coming in, that's its income, and carbon going out, those are its expenses. The whole secret to this puzzle is just understanding how they balance their books. All right, let's start with the income side of things. That's our old friend net primary productivity, or NPP. So a plant sucks in a bunch of carbon through photosynthesis, right? But it can't keep all of it. It has to use some of that carbon as energy just to stay alive. That's called respiration. Think of it like its own living costs. What's left over after it pays those costs? That's the NPP. That's the profit, or net income it can use to actually grow. Yeah, this formula here makes it super clear. We start with the gross primary productivity. That's all the carbon captured. Then you subtract what the plant uses for respiration, it's R value, and boom, what's left is the NPP, the net carbon that actually gets stored as new growth. Okay, so that's the income. Now, what about the expenses? Well, for an ecosystem, the biggest line item on the expense report is decomposition. As soon as something dies, a leaf falls, a tree topples, a whole army of bacteria and fungi jumps on it. They break it all down, and in the process, they release that stored carbon right back into the air. And this is where it all clicks into place. We're going to do a side-by-side comparison of two wildly different places, the steamy hot rainforest versus the icy frozen tundra. First, look at the income, the NPP. It's just a blowout. The rainforest's bar is huge. Its productivity is off the charts. Now look over at the tundra. With its super short growing season and harsh conditions, its carbon income is, well, it's tiny, barely anything in comparison. But then, look what happens when we check their savings accounts, the actual carbon locked away in the soil. The whole thing flips on its head. The tundra, the ecosystem with a tiny, tiny income, has this massive bank of carbon stored up. And the rainforest, our big earner, it has surprisingly little saved away. This is the core of the puzzle. How is this even possible? It all comes down to one thing, the rate of spending. Let's use an analogy. Imagine the rainforest is getting blasted with carbon, like a fire hose filling up a bucket. But that bucket has a giant drain hole at the bottom. The warm, wet environment means decomposition, the drain, is super fast. Carbon goes out almost as quickly as it comes in. Now the tundra, it's just a slow, steady drip of carbon into a bucket. But here's the key. Its drain is just a tiny pinhole. The cold, frozen ground basically puts decomposition in slow motion. So even though not much carbon comes in, almost none of it gets out. It just slowly and steadily builds up for centuries. So this incredible balance has been playing out for thousands and thousands of years. But now, of course, new things are coming into the picture. Powerful pressures that are starting to change the whole equation. One of these new pressures is actually something you might think is a good thing. It's called the CO2 fertilization effect. The idea is simple. With more CO2 in the air, which is basically plant food, plants might just grow faster and bigger, pulling in even more carbon. But, as you might have guessed, it's not that simple. There are a few catches. For one, plants need more than just carbon to grow. They need other nutrients from the soil, like nitrogen, and those are often in short supply. And here's the real kicker. The rising temperatures that go along with more CO2 also hit the fast-forward button on decomposition. So even if the carbon's income goes up a bit, the carbon expenses go up even more, and you could end up right back where you started or even worse off. And of course, there's the most direct impact of all, deforestation. When we cut down forests, we're not just shutting off that carbon income stream, we're also ripping open the soil, which causes all the carbon that was stored there to be released way, way faster. So when you put all these pieces together, what's the big takeaway? What's the final answer to our carbon puzzle? It's actually pretty simple. When we're talking about storing carbon long-term, being busy doesn't mean you're effective. A high income doesn't guarantee a big savings account. The only thing that truly matters is the final balance, the difference between what comes in and what goes out, day after day, century after century. And that leaves us with a pretty heavy question for our future. We've just figured out that these cold, slow, frozen ecosystems are the planet's real carbon vaults. So, as the planet keeps warming and the frozen ground in those vaults starts to thaw, what's going to happen when the doors to the biggest carbon bank on Earth finally swing open?